Let's go ahead and get started.
She did say she's going to do that. She actually wrote it. You're stressing.
Okay, come on now. All right. So, I'm not sure what the obsession with Chick-fil-A is in general, period. All right, so let's talk a bit about Lewis structures. Again, these are going to be how we are going to go ahead and represent how molecules are connected. Okay, you can think of them a bit like if you were trying to figure out where something is, how it's, if you're trying to describe it, one of the steps you would take is this is connected to this, right? Everybody sung that song when they were a kid? The knee bone is connected to the shin bone? No? Oh, that's sad. Do you guys know the knee bone is connected to shin bone? No, there isn't a knee bone. But, yeah. Okay. So when we talk about these Lewis structures, one of the ways you're going to use to generate them is by knowing how many electrons are on the outer shell of these various different elements. Okay? Because what is the thing that's actually going to be used to make bonds, that could be lost, that could actually be interacted with? The electrons on the outer shell, right? Are the electrons on the inner shell going to be able to be interacted with? No. Those core electrons are not going to be able to be interacted with because they're being hidden by the outer ones, right? And so they're too tightly held together. Now, if we know these electrons and we know where they can go, which there's two options. You could either share the electrons. If you share the electrons, those are referred to as bonds. Okay? If you don't share the electrons, they are not being shared, and they're going to be called non-bonding pairs of electrons, i.e. they're not being used in bonds, or another name for that is lone pairs. Okay? They're pairs of electrons that are on one atom alone. Okay? Okay. So again, is everybody comfortable with bonding pairs of electrons and non-bonding? Excellent. Okay. These are typically how they're going to be referred to. Did I already go into my entire thing of never go like that? Yeah. Don't try to represent bonds with just putting electrons there. Okay. So this right here is how you would write a covalent bond. That's how anybody that actually does it does it. This right here is something your book and a few other sources does, and is basically something you need to know it exists, you need to be able to read it, you need to be able to understand it, but frankly speaking, nobody would ever actually do that. It's a really dumb way of doing it. Okay? And so, what are we looking at when we're looking at those, by the way? Right. What's the electrons in between the two fluorines? They're bonding ones, aren't they? They're a pair of bonding electrons. They're being held by the two fluorines together. And so these double electrons in the middle here, those are bonding electrons. Over here, it's represented by a line. How many electrons is in that bond? 2. Every time we see a line, we see how many electrons? 2. Excellent. Now, I'm going to say something that's actually been proven to be wrong by the newest research. But for your level of chemistry, it kind of needs to be that way. Okay? Because it's just too much complexity if we go into what actually exists. Okay. So, when you have a bond, it's always going to be 2 electrons. Is that okay? Anybody want to let that settle in their heads real quick? Okay. Now, full disclosure, it's been predicted and confirmed like 2.5, almost 3 weeks ago now, that you can actually make bonds with carbon that only have 1 electron in them. So, but for your level of chemistry, you're never going to see that. You don't have to worry about it. Just basically it doesn't exist, okay? Okay. If you want to go more advanced, there's some crazy stuff going on. It's pretty incredible. Okay, So how about these electrons up here? Everybody sees pairs of electrons not in a bond? What are those called? Lone pairs. Yeah, they are not involved in bonding, or another way of referring to them as non-bonding pairs of electrons. Okay? You can theoretically have less than a pair for these non-bonding electrons. But for most of the stuff you do, it's going to end up always being in pairs. Okay? Especially these early steps where we're doing the Lewis structures. Now, one of the reasons that fluorine always gets used for this is because fluorine is what's called a diatomic molecule. What that means is these molecules right here, hydrogen, nitrogen, oxygen, fluorine, then chlorine, bromine, and iodine. See how they make sort of an L shape on the periodic table? If you have a pure sample of these gases, you cannot actually have the individual atom, unlike most of the rest of the periodic table, where you could have individual atoms floating around by themselves. Okay? These actually always combine to make molecules, and you always get things like H2, O2, N2, etc. Okay? Anybody have any questions about that? No? All right. It's a semi-memorization thing that you have to do. Like, does everybody understand what I'm saying when I say semi-memorization? Yeah, you don't exactly have to memorize all of them, right? You more have to memorize the pattern, and then you could get all of them. Okay? All right. So this right here is a Lewis structure. This is the way that it's fine if you do this digitally like that. Your book will show you those quite often. Do not write those down on a piece of paper. They won't make any sense. Okay? Okay, so how do we tell how many electrons something normally has in its valence shell? Anybody remember? The periodic table, yeah. Specifically, we go ahead and count. We can usually take the groups. Remember, there's the 1A, 2A, 3A, 4A, etc. That's usually the fastest way to do this. Group 4A has how many valence electrons? 4, exactly. 7A has? 7. You got it. The other way you can do this is your book is going to refer to these as octet and duet, or the octet rule. Many books do. I absolutely hate the terminology. It only works on periods 2 and 3 because everything else has more than 8 electrons when it's full. Okay? But for the most part, most of the stuff you do is going to be periods 1, 2, and 3, and so it works okay. Okay? However, a better terminology for this is Nobel-like. Literally, it takes on configurations that are like the nearest noble gas, right? Okay. And so, for example, hydrogen wants how many electrons total? So we look at the periodic table. 1, right here, 2. So hydrogen wants to be full, 2 electrons. Exactly. If we come here, how many electrons does an oxygen want to be full? 8. Because if we count across here, there's 8 electrons if you're the nearest noble gas, right? Okay. And third period, that works out like that as well. Okay? All right, so the thing I want to point out real quick is there's a shortcut here. How many bonds does a fluorine normally want? Or how many electrons does a fluorine normally want? Oh. Did you bring breakfast for me?
Yeah, I got it.
Okay, fantastic. All right, so how many electrons does a fluorine normally want? It's one step from a noble, right? So it wants 1 electron. Oxygen wants 2 electrons because it is 2 steps from a noble. Exactly. How about carbon, by the way?
4.
Yeah. You can actually go both ways, right? So it wants 4 electrons or it wants to lose 4 electrons. Okay? Carbon is actually kind of an interesting thing. You can have a lot of different states of carbon, and that's why carbon's the basis of all life on the planet. Okay? And there's all these really crazy structures of carbon. like proteins and DNA. Okay. So, how many bonds would that equate out to, by the way?
4.
Yeah, normally 4 bonds. Why is that? Because every bond is typically made of one electron that's provided by the atom in question, right? An electron from another atom, okay? And so there is a shortcut that kind of helps you out whenever you're trying to draw these things out, that you can always look here, go carbon wants 4, nitrogen wants 3, oxygen wants 2, right? Okay, this right here then, hydrogen right here has 1 electron and it wants to get up to 2 electrons, right? Or another way of saying that, wants 1 bond, okay? Carbon here has 4 electrons on the valence shell and it is going to want how many more electrons? 4 more normally, right? Or another way of saying that is it wants 4 bonds normally, okay? Okay, whenever we do a Lewis structure, I'm going to go ahead and go through the rules right now. I'm going to give you rules that if you follow them correctly, you'll always get a Lewis structure that is a valid Lewis structure, okay? Has anybody ever been taught this stuff before? Yeah? Okay. When did they try to teach you to choose double bonds and triple bonds? Towards the beginning or at the very end? They taught you a method that you can fuck up. So, always choose your bonds. I'll just go through the deal. Okay, in this case, we're going to go ahead and do methane right here. And so, again, we have 4 electrons for carbon, okay? And then we're plus, there's 1 electron each for each of the hydrogens, and there's 4 of them, okay? So our total number of electrons is 8 electrons that we have to account for, right? We're going to do this because we have to fill in 8 electrons. Can we fill in less than 8 electrons? No, those electrons have to go somewhere. Can we fill in more than 8 electrons? No, we only have 8 electrons, right? And so our Lewis structure, to be valid, has to incorporate those 8 electrons as stably as we can get, okay? Now, we have 8 electrons to fill in. How do we select the thing that's going to be in the middle? Well, I gave you a version of it right there, but how do we select it? Oh, I just can't hear anything over. We look for the thing that wants the most bonds, that wants the most electrons, okay? That thing's going to have to make the most bonds, and it makes sense to be in the middle, doesn't it? Right? And so the thing that's furthest from a noble gas is what? Carbon or hydrogen? Carbon. So carbon goes in the middle, okay? Okay, now this is a molecule. The things have to be attached somehow or else it wouldn't be a molecule, right? That seem fair? Okay. So the next thing we're going to do is we're going to fill in stuff around that based on how many bonds it wants, okay? Hydrogens typically want how many bonds? 1. We'll only ever make single bonds in this step, okay? Never make a double bond, never make a triple bond. This is where I'm diverging from any of the previous people who have probably taught you, okay? And the reason I'm doing that is if you move it to the end, you can never mess up, okay? You have to get it right. You don't have any choices. Okay, so we put in 1 bond going to a hydrogen. We're going to put another bond going to another hydrogen, right? Why am I not putting a hydrogen bonded to this hydrogen over here?
It's already noble-like.
Exactly. It's already noble-like, or another way of saying that is it has its number of bonds it normally wants. Okay? Okay, and then I'm going to keep doing that until I run out of my hydrogens. All right. And so in this case, we've actually completed our molecule. But we have to check this, okay? Okay, so first thing you're going to do now is now that we've put in these hydrogens, we're going to go, how many electrons have I used? So each bond has how many electrons? 2. There's 4 bonds, and that is 8 electrons. And so notice we have now used up our electrons, haven't we? Okay. All right, so the next thing we have to do is everything noble-like. All the hydrogens, are they noble-like? Yeah, they're all noble-like, aren't they? The carbon, is it noble-like? Yeah, 8 electrons, it's noble-like, isn't it? Okay, once these things have been done, we've used up all of our electrons and everything's noble-like, we're correct. We got it. Okay? In just a bit, I'm going to do one with a double bond and some more electrons, okay? And we'll get the next steps. Keep those previous steps for now in your head. Don't worry, we'll get practice. We'll get practice. Okay, so these are some Lewis structures for some common molecules here. Let's go ahead and do water real quick, because water is a pretty simple one and it's useful. So you would get H2O. And H2O, how many electrons do we have? Oxygen has 6. Hydrogens each have 1, so that's 2. 8 is correct. Okay, which one goes in the middle? Oxygen. You got it. Okay, which ones get filled in around it? Hydrogens. So we bond hydrogens to it. Okay, so we have used how many electrons now? We've used 2 sets of 2, haven't we? Yeah, so 4. That leaves us with 4 remaining, doesn't it? Okay, so the next step is you would take any electrons you had remaining and you would fill in the atoms on the outside of the molecule. Leave the one in the center alone. Okay? Now, we look at the ones on the outside. Hydrogen, does that need any more electrons? No, it's full. The other hydrogen, does that need more electrons? No, it's full. So in this case, we didn't actually have to put any electrons in those, did we? Okay? But if we had something like a fluorine, we would, wouldn't we? Yeah. Okay, so the next step after that is going to be, I'm going to take any remaining electrons now, and I'm going to put them in on my center atom. Okay? They're going to come in as lone pairs. And so I'm going to make little lines, because if I make dots, it doesn't show up well. And so that's 2 and 4. Okay? That gives me 8 electrons on that center atom, which is a noble-like configuration, right? And I've used up my remaining 4 electrons, haven't I? Okay? And that now is the structure. Everybody okay with that? Okay, fantastic. Fantastic. All right. So how about double and triple bonds? Double bonds, what are they? Yeah, 2 lines, and they represent how many electrons? 4, exactly. Every line is 2 electrons, isn't it? Okay, a triple bond is going to happen when you share 3 pairs of electrons, right? Okay, and that means it's 3 lines. It's going to be 6 electrons total. All right, so let's go ahead and do carbon dioxide. This is going to have a double bond. So what's the first step we do? Count the electrons. Okay. Carbon has how many electrons? 4, thank you. Oxygen has how many electrons? And there's how many oxygens? 2. So that's times 2, isn't it? Okay. Now, that's going to give you 12 plus 4, 16. And that is the number of electrons I have to account for, isn't it? Okay. Everybody good so far? Fantastic. Please let me know if you get lost anywhere here. This is actually going to be pretty important for this next part. All right, so which one goes in the center? Carbon, because it has the most connections it needs, doesn't it? Which one's going to get surrounding carbon? Oxygen. We'll make single bonds to everything first. Don't bother putting in double or triple bonds yet. Okay? Okay. All right, so what's the next part? We've used up how many electrons? 4. We have 12 left. And so now we fill in. Where do we fill in the electrons now? Do we fill it in on carbon yet? No. No, we're going to fill them in on oxygens first, right? Okay. Okay, so how many electrons does that oxygen need to get noble-like? 6 more, right? Yeah. So oxygen, to be noble-like, is going to be 8 electrons. We have 2 electrons on it right now, don't we? Okay. And so that's 4 on it now, 6 on it now, 8 on it. Everybody okay with that so far? Okay, the other oxygen also needs the same treatment, doesn't it? So we go over here, we do that. Okay, so how many electrons have I now used? Yeah, I've used all of them, haven't I? Yeah. So I've used up all my electrons. I'm now done with my electrons. I can't put any more. Is everything noble-like yet, though? No, it is not. Okay. So what you're going to do now is you're going to move lone pairs from around into bonds until everything's noble-like. So the stuff that surrounds it, you're going to move those lone pairs into bonds to make everything noble-like. Okay? Okay, so that's going to end up giving me a double bond here and a double bond right there. Now, how do I decide which side to go ahead and move electrons into bonds for? Because I could have moved 3 bonds on one side, 1 bond on the other, right? Like, that could have been something. That would have been an option. How do I decide that? I'm going to try to even everything up as best I can. Okay? Try to achieve some symmetry. Now, is the other one wrong?
No, it's just not.
Yeah, it's not wrong at all, actually. Actually, it is absolutely correct. And it's something called resonance, which we're not going to get into in this course. We just don't have time to go into all that. But if you wanted to learn about it, come join me in a more advanced chemistry course, okay? Okay. So, again, we had 4 lone pair electrons, 2 lone pairs, giving you 4 electrons in each of the oxygens. This one would only have like that, by the way. So, that is our final structure right here for our Lewis structure. Notice that we have 8 electrons on each of these. Okay? Everybody understands where I got those lone pairs from? They're just the ones from the previous. Okay. This is actually the big difference between this mechanism, the style I'm teaching you to draw out Lewis structures, and most other styles. Because I do this step where I take lone pairs and put them into bonds, I can't actually get this wrong. It's not possible. Yeah. As long as I follow the steps, it doesn't matter if it's a 3-day bender and I did this at 4 o'clock in the morning, I'm going to get it right. Okay? Okay. So, anybody have any questions about writing CO2? Okay. All right, so there is exceptions, of course, to the octet rule. Specifically, they happen on periods 3 and 4 the most often, is where you're going to run into them, okay? And this is the extra octet is actually what that's rule is called. It's going to be the nonmetals P, S, Cl, Br, and I that you're going to see this the most on. And what's going to happen is they're going to get valence electron numbers that are in the 10 and 12 electrons. For example, sulfur normally has octets, however, SF6 actually has 12 valence electrons on that sulfur. And why this happens is actually because the d orbitals are actually available for bonding on the 3rd and 4th periods. So it actually has the space for the electrons, They're just weird spaces that take a lot of energy. Okay? And so you don't see it as often, but it can happen. Okay? And that's the big hint. If you see a central atom that's on the third or fourth period, you can get 10 or 12. Okay? You're never going to get that up here. You don't have spots for them. All right. So let's talk about electronegativity. Electronegativity is how well something holds on to its electrons, or how well it pulls the electrons when it's bonded to something. Okay? The electronegativity trend is actually very similar to the size, ionization, metallic character, all of those things. And so as we go up and to the right on the periodic table, we are going to experience larger and larger electronegativities. Okay? Fluorine being the biggest one, oxygen being the next after that, and then nitrogen and chlorine being tied for the next place. Okay? After that, the differences in electronegativities go down a lot. Right? There isn't as much difference going across or down versus those ones concentrated in the corner. Those are very, very strong electronegativities compared to the rest. Okay? Okay, so again, higher electronegativity as we go up and to the right. Anybody notice something about the noble gases? They don't have these numbers, do they? No. Why wouldn't noble gases have electronegativities? They don't bond, yeah. Yeah, so we can't measure how well it holds on to electrons in a bond if it doesn't bond. Yeah. And so if you could get them to bond, which you actually can in very weird situations, they'd be very high. Okay? But for the most part, they do not bond. So your book, electronegativity value of an element, indicates the attraction of an atom for the shared electrons in a bond. I think you guys got the trend okay. Does anybody have any questions of the trend? Fantastic. Fantastic. Anybody notice something about this trend? So why is something a metal? Loses electrons easy, right? Why is something a nonmetal? Holds on to its electrons, doesn't it? Yeah. Yeah, this was actually why things were metals and nonmetals, and why we had ionic compounds. They were losing electrons, all that stuff. Okay? So let's talk about the polarity of a bond. So we have ionic bonds, right? Everybody remembers that? We just lose an electron to another. So a metal loses an electron to a nonmetal. Okay. We have covalent bonds, and in that case we share electrons. But because you're sharing something, does that mean you're sharing it equally? Who here played with other kids when you were a kid? Okay. Who here, every single thing you were supposed to share, it was shared equally? Most definitely not, right? Never. And so in bonds, of course, this is also true. If you're sharing the electrons, one can hold on to the electrons better than the other, then it's going to end up with those electrons around it more often, isn't it? Just like if you put two toddlers with a single toy, what happens? The one that can pull better typically ends up with the toy, right? Yeah. Okay. This is what happens when you have two things with equal strength. They will share those electrons equally. Neither one can pull it from the other. And so you end up with sharing equally finally. Okay? When you have a difference in electronegativity, what's going to happen is the more electronegative thing is actually going to pull the electrons over onto it, and this is going to cause it to be partially negatively charged. Okay? The other thing where the electrons were pulled away from it is going to end up being partially positively charged. Remember, electrons are negative, aren't they? Okay. And so everybody see this symbol here? Looks a bit like an 8 or something? Like a really weird 8? Okay. That is the lowercase delta. Okay? You know the Greek alphabet delta? Anybody know what the uppercase one looks like? Seen that? That's the uppercase delta. Okay? They both mean change. So uppercase delta means full changes. Okay? Lowercase delta means partial changes. Right? And so in this case, we're going to have partial charges because we're not going to fully lose electrons. That making sense? Fantastic. So this is one way of representing having these partial charges. We put this lowercase delta plus lowercase delta minus. All right. Anybody notice this is now has poles like a magnet, right? Positive end, negative end. Okay. This is referred to as bond polarity, or a polar covalent bond. Okay. Okay. As in like two poles like a magnet, right? Okay. Okay, so again, a nonpolar covalent bond is going to be where you have two nonmetals. They're going to share the electrons essentially equally. Okay? There's not a noticeable difference in where the electrons are getting pulled to. And so these are examples of nonpolar covalent bonds. Notice the difference is very small. It has to be 0.3 or lower. Okay? That's the difference in the electronegativities, isn't it? Okay. When we have a polar covalent bond, we're going to have a moderate difference in electronegativities. So this is going to be a difference of usually somewhere in the order of 0.4 to 1. Usually it's like 1.4 or 1.5. There's actually arguments on this. But in general, it's a moderate difference in electronegativity. Okay? And why does it need to be moderate? So you need to be strong enough to pull the electrons over towards you, right? But what if you're too strong? You just pull the electrons completely, don't you? And then it's not covalent, is it? It's an ionic bond. Mm-hmm.
On the non-polar covalent bonds,
Mhm.
what did it say about the electronegativities?
0.3 or lower.
Okay, thank you.
I'll re-summarize this, by the way. Don't worry if anybody's... Yeah, I have a handy-dandy little table that will have it. Yeah, so you can think of this a lot like... has anybody ever seen tug of rope? Where two groups tug the rope, there's a little flag in the middle? Okay. If the two groups are the same strength, you don't get any difference, right? If they're basically the same strength, they'll stabilize mostly on the middle, right? And then what if the groups are a little bit different? Then the rope tends to move one direction and stay there for a while, doesn't it? Okay? And finally, if one group completely overpowers the other, then they just pull the whole rope and the other group just goes flying, right? Yeah. Okay. So again, these are polar covalent bonds. They're going to be called dipole, di meaning two, and so literally they make two poles. Now, one of the things I need you to have in the back of your mind here is that bond polarity specifically is for bonds. This is a bond dipole. These are going to be for individual bonds. Okay? Because I'm going to introduce molecular dipoles in a bit, right? Which are the summed up bond dipoles. Okay. So this is the methodology of writing it out that we had talked about before. The easier methodology that almost everybody always uses is they put a plus mark where it's positive and an arrow where the electrons are going towards, which is the negative end. Everybody okay with that? Okay. This is the far, 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 far more common way of doing it. Okay? Basically, you will almost never see the deltas unless it's some reason necessary. Like it's a structure where the arrows can't fit. Yeah. All right. And so if you have a very large difference, in this book it actually defines it as 1.8 or larger. This is going to be an ionic bond. Okay? Because it's just going to tear the electrons away from the other atom. Okay? Okay. And so these are the summed up differences, so you can write them down here. Okay. There you go. And they're on my slideshows if you ever want them. The new slideshows are at the bottom because of how things get organized. Okay, so these again are going to be the electronegativity and bond types. Keep in mind that this is a sliding scale, okay? And so you have more or less evenly shared, which is nonpolar covalent. You then have polar covalent, where the sharing is not even, but still being shared. And then you have ionic, which is where it actually tears the electrons from the other, and they are now separated. They're just attracted to each other because one's negative, one's positive. Okay? Okay. Please make sure you are, whoops, I am not logged in now. Oh, weird. Why it's doing that. Man, I got kicked out. Okay. There we go. Okay, everybody, please join me in the Slido classroom. We'll have a quiz coming up in just a bit. If you can't do the QR code, that little link right there, that number, can just be typed in, and then you'll join me in the classroom. Okay. All right. So, use the electronegativity differences. You can actually mostly just predict these, because most of the electronegativity differences are actually quite predictable. But use those electronegativity differences to do the nonpolar covalent, polar covalent, or ionic between these different options right here. And so we're actually going to do the quiz for polar covalent first. Okay? So get in your head, which ones do you think are polar covalent? Everybody ready? Okay, come on. You can do it. Okay. Which ones were polar covalent? Everybody have the ones they think are polar covalent in their heads? It could be multiple. It won't be until I go on to the next one. Yeah. Okay, ready? Okay, everybody joined and everybody seeing the quiz? Nope, it won't show up until the next one. You'll have 15 seconds. That's why I gave the problem to you beforehand. Is so you guys can have ones in your head already ready. Ready, set, go. Okay. Didn't go through? Okay. Make sure you're joined. If you aren't already joined in my classroom. Oh, do you have a computer or?
My computer's not running either, that's why I don't
Okay. Talk to me after and we'll. Yeah. Okay. Everybody. Okay. Did it go for people? Okay. And that is actually correct. Good job. Yeah. So, Kn, metal and nonmetal, right? That one has to be ionic. ClCl, same thing. That can't be polar, can it? Yeah. The other ones, NO, HCl, This is a trick that's commonly played in these questions, by the way, is the non-polar covalent ones are typically the same both, so that we don't have to give you a table, right? Very, very common in any testing of this. These ones here, one of the things you can help yourself out with, if it's two things up on the top right, you know, chlorine, oxygens, nitrogen, fluorine, those things are all 0.5 steps. So, okay, let's go ahead and do the ionic bond next. Which one's the ionic bond? Did you pay enough attention to me to hear it? Go ahead. Is it working now? No?
Just tried to refresh it.
Okay. Shit. Wow. Good deal. That is funny. There's an HCl. Okay. All right. So, yes, just like I went over, the chlorine would be the nonpolar. All the other ones we got. Okay, let's go ahead and do shapes of these molecules. So before we did the Lewis structures, that told us how these things are connected. Okay. Now we're going to predict the shape of these. So if I took 4 balloons and they were pushing each other apart and they were trying to achieve the furthest apart they could get, how would those arrange themselves? What shape would they take on? So they'd take on something that looked a lot like a camera tripod, right? Okay. Kind of like this. See how it looks like a camera tripod? Okay. And the reason for that is a camera tripod is attempting to have 3 feet, that's as far apart as possible, so they can get the most stable base, right? And then it has a top that they're trying to get as high as possible, right? And so they're actually trying to maximize the separations, aren't they? Okay? Now, if you put 4 things that are negatively charged near each other, what's going to happen to them? They're going to push each other away, aren't they? And they're going to try to maximize the separation between them. Okay? And so this is how you can actually predict the structure, the shape of any molecule, is because the different atoms in it are always going to usually have a central point, right? They'll have an atom in the middle, and they're going to try to maximize their separation from each other around that central point. Okay? Okay, so let's talk about what the theory is called. By the way, this gives you 109 degree angles in case you're curious. This shape is called the tetrahedral shape. You can actually see this is a tetrahedron, and so tetrahedral. Okay? And yes, it does look like a pyramid, but you got to remember a pyramid has 4 sides. Okay? 3 sides on the top and then 1 on the bottom, right? Okay. Okay. Very good. By the way, whenever we look at these are how you write these out. They're called a wedge dash notation when you're trying to make them look 3D. Okay? What does the solid wedge mean? What does it look like it's doing? Yeah, it's coming out towards you. Yeah. This dash, what does it look like it's doing? Fading away from you, right? Yeah. And so the dash is fading away from you. Anything that's a solid, just normal line, those are in the plane of the page, or in this case, the screen. Okay. Okay. This is actually a 3-dimensional model. If you're on a computer viewing program, you could actually rotate this around. Okay? It looks a bit like a video game model because it basically is. Yeah. By the way, do bonds actually have like lines or little, are they physical structures that hold things together? No, they're just areas where electron density is highest, right? Yeah. Okay, so this theory is actually called Vesper theory which stands for valence shell electron pair repulsion, which actually tells you everything I just told you about it, but in a way that's a little bit less comprehensible. Okay? So, Vesper theory. And all it's going to do is just predict the arrangement around a central point due to the fact that these things are repelling each other. Okay? To do that, we're going to have to talk about something that your book is going to call electron groups. Most texts actually call them electron domains, which is a better terminology. Because what does domain mean? An area which something has control of, right? Whereas group doesn't necessarily occupy an area, does it? Yeah. But, oh well. You're going to repeatedly catch me falling into domain because that's far better terminology. Okay? But your book calls it electron group. Right? Is everybody good with that equivalence right now? Okay. 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 So when we have two things around a central point, what's going to be the maximum separation? By the way, if you guys get balloons that you can blow up, you can actually tie off their stems to each other to give you a central point, and it will perfectly predict all these structures because the balloons will push each other to the farthest extent they can. Okay? So, two things pushing each other away, but they're attached to a single point. What are they going to give you? Yeah, they're going to give you a line, aren't they? And this is going to be called linear. This is actually what CO2 looks like, by the way. So that is linear. How about three things around a central point? What is that going to do? A triangle, yeah. A triangle on one plane, right? Okay. If you were to try to name that, it would come out something like trigonal planar, right? Yeah. Yep. Okay. And so this is actually formaldehyde, by the way. Huh? Formaldehyde? Yeah. You know, the funny thing is, have you guys ever seen the like creepy gravedigger trope? Cemetery guy? Like puffy red eyes, right? And pale, kind of stooped over, always lethargic. Do you know why that trope is like that? That's formaldehyde poisoning. Yeah. The same thing happens to you if you have new house materials that have not been properly rested and treated. This happened to a bunch of houses for the last 20 years because some of the materials from China have been not properly rested and treated. And that's actually called new house syndrome. People oftentimes think they're possessed because they move into a new house. They start becoming aggressive. Their head hurts, like a pounding headache. Their eyes become red. They're lethargic, like they're fighting something off. I'm not joking at all. It's called new house syndrome. Look it up sometime. It is one of the leading causes of people thinking that they're possessed or that they have a ghost. What's the type of ghost that possesses people? Poltergeist? Yeah, poltergeist. Yeah, like the movie. No joke at all. This is an actual thing. People mistake it for possession and call in like priests and witch doctors and all sorts of stuff. It is wild. And it is formaldehyde poisoning. Same reason that like the mortician trope always has that look. Yep, that's formaldehyde poisoning as well. Whoa, huh? You didn't think this would go there, did you? Okay. Okay, so what if you have something that is getting pushed into an angle? So in this case right here, this is the Lewis structure. Everybody see that okay? Okay. Now before, we never had to worry about whether these things were just electrons or if they had something at the end of it. See that? They always had something at the end of it. They always had atoms at the end, didn't they? Okay. And so let me go ahead and go through the rules now, since now we have to actually understand these things a bit more. Now, these are electron domains. They are where electrons are. They could be a single bond, they could be a double bond, they could be a triple bond. They could also be a lone pair. That's also an electron domain. Okay? Literally, there are places where electrons have to be. And that's because the electrons are going to repel each other, right? Yeah. So it's actually quite simple in its essence, isn't it? Okay. And so when you're doing the electron group geometry or the electron geometry of a molecule, you're going to do this for just the electrons. It doesn't matter if there's something at the end of it. Okay? But when we're talking about a molecular geometry, that's going to be the geometry of the molecule, not just electron groups that don't have anything at the end of them. Okay? And so this right here would be the electron geometry, and that one is 3 different groups. That's going to be trigonal planar, isn't it? Okay. Now, if we want the molecular geometry on the other hand, we will not count this lone pair right here. Okay? Because that doesn't have any atom at the end, does it? Right? So this is then going to be this shape right here, which is called bent. It be bent. Okay? You have to do a weird thing where you don't actually use proper dialogue. So, because it is so funny they called this bent, right? Everything else is like very, very correct terminology. This one's bent. It's like somebody got tired of actually using scientific terminology. Okay, so right here we have, again, electron geometry for this. We have 4 different groups. This is going to be tetrahedral electron geometry. It will be tetrahedral for its molecular geometry as well, because there's no lone pairs. Okay. This one right here, again, we have 4 different domains, 4 different groups. And so this one's going to be tetrahedral for its electron geometry. One of those domains or groups, though, is a lone pair, isn't it? And so we're going to take that away from the molecular geometry, and this is going to be what's called trigonal pyramidal. Can everybody see the difference between trigonal pyramidal and trigonal planar? One's not in the plane, right? The other one's flat. Okay. Okay. Now, this one again, here we have water. That's the Lewis structure that we came up with before. That has 4 different domains, doesn't it? So what's the shape? So the electron geometry is what? Tetrahedral. 4 different domains, tetrahedral, right? The molecular geometry, though, is what? Bent. Exactly. Because we don't count the lone pairs, do we? Okay. And so the remaining shape is just the bent shape. Okay. This right here is actually a summary of these things. You'll notice again, these are the bonded ones. These ones right here are the lone pairs. Okay? And if you added those together, they're always going to give you the number of electron groups around it. Right. Okay? Anybody have any questions about that so far? Okay. So the full procedure for figuring these things out from, say, a molecular formula is going to be what? Lewis structure first, right? And then we're going to have to take that Lewis structure. We're going to have to figure out the number of electron domains around it. That's going to give us our electron geometry, right? Subtracting lone pairs, that's going to give us our molecular geometry. Okay? Okay, fantastic. So the Lewis structure here, did anybody want to learn the fast way to do these things? Okay. There is a trick that you can play that will make everything a little faster, and that's, remember how I was saying things want this many bonds? If you look at your periodic table, they tell you how many bonds things typically make. Okay. Sulfur typically makes how many bonds? 2 steps from a noble, right? And so it usually makes 2 bonds. Got it. Hydrogen usually makes how many bonds? 1. And then all I have to do is just take my remaining electrons. Sulfur had 6 electrons, right? It used up 1 in each bond, and so it has 4 more electrons around it. It's just a hack to make things faster. Okay? It uses the same procedure actually as the other way. It's just I need to understand what I'm looking at better, don't I? Okay? Right. If you practice and get used to these things, you'll end up probably doing that at some point. If you had trouble with what I just did, don't try it until you've done the other way and you built up some experience, okay? Okay. Okay, anybody have any questions about my Lewis structure? Okay, how many domains does it have? 4 total, you got it. 2 bonding, 2 non-bonding, right? Okay. Electron geometry. So molecular geometry, electron geometry. So the electron geometry is tetrahedral. That's everything, right? That's the 4 domains total. Okay? Okay. Now we take away those 2 domains that were the lone pairs. That one's going to be the molecular geometry, which is bent. You got it. You got it. Okay. So let's state the number of electron groups, lone pairs, and then use the Vesper theory to determine the shape of the following molecules or ions as tetrahedral, trigonal, pyramidal, or bent. So what do we got here? PF3. Okay. So try to do the Lewis structure if you're unsure. You can also do my quick hack. It works for most of these quite well. Okay. Okay. So how many electron domains? 4. Yep. 4 is correct. Okay. Let's go ahead and do the Lewis structures real quick. Did everybody get that for the Lewis structures? No? Okay. So we have phosphorus here. That's typically 3 steps to a noble, right? Okay, going left. Okay. And then we have fluorine. That's typically 1 step to a noble, isn't it? So we have the P in the middle, 3 fluorines to it. The fluorines get 6 lone pairs on each one. The phosphorus gets 2 electrons to it. Okay. Okay. And so what's the next one here? Notice this one's basically water with sulfur instead. Yeah. Okay. By the way, does anybody know what this one is in terms of things that you've experienced in life? Okay, anybody smelled the smell of rotten eggs, farts, getting natural gas when you turn the tap on? Those are all hydrogen sulfide. This. Yeah. The hydrogen sulfide, by the way, is added to the gasoline, the natural gas, so you don't like it when it's on. To get people to turn it off. Yeah. Okay, how about this one right here? We have a carbon in the middle and 4 chlorines around it. Everybody okay with that one? Okay. Okay, number of electron domains for the first one, PF3. 4, exactly. Huh?
How is it only 4?
It has 1 here, 2, 3, 4.
Then what about all the ones around fluorine?
They don't matter because they're not going to take up space around that central one.
Okay.
Okay? So, for example, like everybody else that's sitting around you, doesn't affect how you sit in your seat because they're too far away, right? On the other hand, your bag affects how you sit on your seat, isn't it? And so does the desk, because those are taking up space around you. Okay. Okay. Okay, so we have 4 groups, or 4 domains, and then that's going to give us a what electron geometry? Tetrahedral, exactly. What sort of molecular geometry is that going to give us then? Close. Trigonal pyramidal. Yeah, it's a 3-dimensional one. Yeah. If we just had 3 electron domains, period, no lone pairs or anything, that would be the planar. Okay. And so how about this next one? What's the electron geometry? Tetrahedral. Number of electron domains? 4. Bonding ones? 2. Non-bonding ones? 2. Very good. And the molecular geometry? Bent. Oh, you guys gotta go the extra mile. It be bent. Okay. How about this one? Tetrahedral, just straight up, right? Yeah. Yeah, no difference between electron and molecular and blah, blah, blah. Okay. Okay, so let's talk about polarities. Remember how bonds can have polarities? Okay. And so each bond, if there's a difference in the electronegativities, can have polarity, a positive and negative end, right? So what if you start combining these into entire molecules? Well, depending on the geometry, they could either cancel out, which is happening right here, and so you have no overall you have no overall dipole for the molecule, right? Despite the fact that all the bonds are polar, right? Because they're all pulling in different directions and canceling each other out, aren't they? Okay? And so those are going to be polar and nonpolar molecules, or otherwise known as a molecular dipole. Okay, whether it has a molecular dipole. Okay. So if we have polar bonds, does that mean the molecule is going to be polar? Okay. If we have all nonpolar bonds, can the molecule ever be polar? No, no. The molecule is always nonpolar if all the bonds are nonpolar, okay? But if we have polar bonds, they can actually cancel each other out and give you no overall dipole, okay? Giving you a nonpolar molecule, a molecule without poles, okay? All right, CO2 is actually a really good example of this. It's a nonpolar molecule, despite the fact that the oxygen and carbon, both those bonds have dipoles, don't they? But because they're pulling in different directions, they cancel each other out. Okay. Okay. CCl4 is also another good example of this. Again, they all cancel each other out. These are all nonpolar molecules, meaning they don't have an overall poles. Okay? They don't have an overall molecular dipole. Now, the next one is going to be for polar molecules. These ones are going to have overall molecular dipoles. Okay? You can think of these in your heads as little magnets. Has everybody played with little magnets as a kid? And you had a bunch of them, and you threw them in like your play pack with all the other toys. What do they always do? They always snap together and gather together, don't they? And then you gotta untangle them all. Okay, good. Now we have that idea in our head, so when we get to the solutions, we can work with them. Okay. Okay. Now, polar molecules, HCl being a great example. These are going to be polar because their bond dipoles are not being canceled out. Okay? And so again, they have an overall dipole. They're little magnets. They're positive and negative ends. Okay. This is another one that's a polar molecule. This is actually water. This is why water has a boiling point of 100 degrees. This is why water does all the things it does. Okay? Interestingly enough, anybody notice the shape of a water crystal? What does a snowflake look like? Little hexagons, right? Everybody's seen something like that? Yeah. The reason it looks like that is because the water molecules are actually attracted together like so. And so they actually arrange into those shapes because they're bent and they have this bond polarities. So all the stuff that you've always experienced in your life, why is it being caused? By these things we're talking about right now. Okay? Okay, anyways, again, this one actually partially cancels out its bond dipoles, but notice there is one end that would actually add together, right? And so your overall dipole is actually going like this, up this way. Everybody okay with that? Fantastic. Okay, this one right here is ammonia, actually. Ammonia, again, is going to be polar. All right, now let's determine whether something is polar or non-polar. Everybody ready for it? Okay, I'm going to give you OF2. Oxygen with 2 fluorines on it. Okay. Is that polar or non-polar? Everybody got something in their head? Ready? Set. Go. Ready?
I'm not seeing it.
No, you won't see it until the next one. Sing it now. Does everybody see it and able to answer?
I answered, but I don't know.
Okay. So that one is polar. And the reason for that is the oxygen and fluorine has a bond dipole. Okay? Fluorine is the big bully. It takes the electrons from everything, okay? And so when you look at oxygen and fluorine, you're going to get something that looks like this. I'm not going to bother with the lone pairs. And it is bent. It has bond dipoles. They go like so. Anybody notice it's basically reverse water? Yeah.
Would they both be pulling on it equally if there's 2 of them?
In the right and left directions. But in the top and bottom, they actually are adding up.
Okay.
And so you have one end that's positive, the oxygen, one end that's negative, the fluorine end. Okay? It's actually reverse water, if you will, for its bond dipole. Yeah, looks a lot like the water, just the fluorine is the more electronegative one. Okay. Okay. So let's identify each of the following molecules, polar or non-polar. Okay. All right. So, PBR, what's that one going to look like? Yeah, this one's polar. HBr, polar, yeah. And CF4, non-polar, because that one's going to cancel on all the different sides. Okay? So there's 2 main things you always got to figure out whenever you're figuring out polar versus non-polar, right? 1, do the bonds have dipoles? Okay? Are the bonds polar or non-polar? And then the second thing you always need to figure out is, will they cancel out? Okay? To cancel out, they're going to have to be surrounding it in every direction equally. Okay?
How do you know if the bond has a dipole or not?
If they have a significant difference in their periodic table positioning, and one of them something up on that top right corner, it's going to be polar.
Okay, so we're not
Okay.
supposed to like know that off the top of our head. Like, we have to use the table, right?
Yeah, you'll want to use the periodic table, though you could know it off the top of your head, just because the things that are up in the top right corner are something you probably used enough that you'd be surprised. Yeah. But no, I mean, you always have a periodic table whenever you're doing anything for me. So yeah, I would use a periodic table. Again, these ones, significant difference, bond's going to be polar, right? These ones, the bonds are actually considered nonpolar covalent. I'm sorry, hydrogen would be considered nonpolar covalent. Whoops. Yeah, I have hydrogens for some reason. Anyways, it doesn't really matter either way because this one right here, 4 different ones around it, that's going to be tetrahedral. That's going to all cancel out, right? Okay. The CFs would actually be polar bonds, though. Okay. Okay. So let's talk about ionic bonds. Now, before we had been talking about the scale that goes from covalent to ionic, right? So when we have an ionic bond, what's going to be happening? Well, it's not really a bond like the other ones are, is it? Okay? It's not sharing electrons. These are actually individual particles, aren't they? They're not attached. So what you're getting here is ionic bonds are what are called intermolecular forces. Okay? What's an interstate? Does it go within a state? It goes between states, doesn't it? Internet. Does it go inside your network? No, it goes between networks, right? Intermolecular is forces that attract two molecules together. Okay? And so this is the strongest intermolecular force. It's extremely strong. This is why you've never smelled or seen a salt melt. Okay? Because it's so strong, you're just not going to get them breaking at room temperature, and you're not going to be able to break these connections in your kitchen. Okay? You'd be burning down your stove far before you did this. Actually, you would have melted your stove like 200 degrees Celsius ago for most salts. You actually have to have very special casting equipment for them. Anyways, this is NaCl. It actually melts at 801 degrees Celsius. A little bit warm, isn't it? Okay. All right, so this is the strongest intermolecular force. Very powerful connections. This doesn't necessarily mean it's very strong in terms of taking a hammer to it, as evidenced by the fact that you can break apart salt crystals pretty easy. Okay? But it's a very powerful intermolecular force. Dipole-dipole attractions. Remember where we had these molecular dipoles? Well, when you get two magnets next to each other, what happens to them? They snap together, don't they? Yeah. And the same thing's going to happen when you get two dipoles next to each other, right? Because they're just little magnets. And so they're going to snap together, positive to negative, positive to negative. Okay? And these are going to give a pretty strong intermolecular force. Right here we have a very special case of dipole-dipole attractions. These are called hydrogen bonding. Has anybody ever heard of hydrogen bonds before?
Yes.
What the heck? Okay, what's the time? Oh, 1 minute. Let's go ahead and leave on here. We'll talk about hydrogen bonding next. But in terms of strength, ionic, hydrogen bond, dipole-dipole.
6, right?
Yeah, very in chapter 6. Okay, you all have a wonderful day.
I sorted one of these wrong, but like, because that says trichloride, so 3, and that's the only one with 3. Pentachloride, that's the only one with 5 for chlorine.
Okay.
And then diphosphorus tetrachloride.
Is that 4?
Isn't tetra 3?
4.
Oh, yeah. Okay. Yeah.
No problem. Yeah, I got where you're coming from, though.